This is the video showing how we derive the law of cosines. It's based on a worksheet that we did in that part 2 class. I asked you to go through this worksheet and solve the expression, or find different expressions, do different things. This is basically a summary of what you would do to derive the law of cosines. So first of all, question number 1 says, write an expression for E in terms of B and theta. And you will notice we actually have 3 triangles here. I started off with the triangle of interest, a non-right triangle. And law of cosines, as we will discuss or have discussed, is used for triangles that do not have right triangles. I have added a right triangle to that triangle, and that forms a third right triangle, which also has a right angle, and we are going to use those different triangles to show the law of cosines is valid. So let's start with E in terms of B and theta. E is part of the big triangle, B is part of the overall big triangle, and so is theta. So I'm looking at the large right triangle. I'm finding the hypotenuse, starting at the right angle. I start at the angle that we know, and in this case it's a representation of an angle that we might know in the future. It's still a variable, but it's the angle we're using. That gives us the opposite side. And the side left over is the adjacent side. And I'm going to call that ABJ because we're already using A and D. I'm going to just put an A there. So we'll start now. Have my opposite, E is my opposite, B is my hypotenuse. And I use sine. Sine of theta equals the opposite over the hypotenuse, or E over B. But I want my equation to be E in terms of B and theta. So I have to get E by itself. I have to solve for E. I multiply both sides by B. And I end up with E equals B sine of theta. And I switched it around when we do this, write the expression for E in terms of B and theta, we typically put the E first. So I switched the equal sign. And in number 2, I want to write an expression for A plus D in terms of B and theta. So I have my A plus D. That actually happens to be the side down here. The length of the base of the large right triangle is D plus A. So I can say that A plus D over B equals cosine of theta. Having found my hypotenuse, opposite, and adjacent over hypotenuse is cosine of theta. A plus D over B is cosine of theta. And again, I want to isolate A plus D. So I multiply both sides by B. And I put B before the cosine, so that we know that we do the cosine of theta first, and then multiply by B If I put the b over here, it looks like we multiply b times theta and then do the cosine. That would give us a different result. So I say b cosine of theta. Now that I have those two expressions, we're going to move on and start talking about the smaller right triangle and see what kind of information we can get from that. So, actually, first of all, I'm going to solve for d. Because the small right triangle has d in it, if we're going to use that, we need to solve for d. So I take my expression equals b cosine of theta, the expression that I just did in number 2, and I solve for d, which means get d by itself. I subtract a from both sides, get b cosine of theta minus a. And it's understood that this means do the cosine first and then subtract, actually do the cosine first, multiply by b, and then subtract a. If I wanted to subtract a from theta first, I would put parentheses around that. So this expression means take the cosine of theta, multiply by b, and then subtract a. So I have an expression for d in terms of b, a, and theta. I have an expression for e in terms of b and theta. And I want to investigate what information we can get from e and d in that smaller right triangle. So if I look at that smaller right triangle, I can see that d squared plus d squared equals c squared. So c is actually a part of the small right triangle, but it's also a part of the non-right triangle. And that's going to be very helpful. C squared equals c squared plus d squared. And ultimately, I need to get c squared in terms of a and b. So I have to take my expressions for d and e and plug them back into my expression for c squared. So in problem 4, we found that c squared equals e squared plus d squared. And we know that e squared and d squared can be expressed in terms of a, b, and theta. So I had c squared equals e squared plus d squared. And we knew that e was the same as b times the sine of theta. I could say c squared equals b sine of theta squared plus d was b times cosine of theta minus a. And I will square that. And you will notice in question 6, I technically have an expression now, but it's not in super usable form. It doesn't look like law of cosines yet. So I have rewritten that expression in question 6. B sine of theta squared plus b cosine of theta minus a, that quantity squared. I'm going to simplify that now, get rid of the parentheses. That's simplification means you get rid of the parentheses. So I'm going to take this and I'm going to interpret this literally. It literally means take this b sine of theta, and then whatever you get, square that. And the second part means, sorry. So when we square something, we multiply it by itself. So that literally means multiply b sine of theta times b sine of theta. And then the second part of the expression literally means b cosine of theta minus a. Whatever that answer is, multiply it by itself. B cosine of theta minus a. So now I'm going to do some rearranging. B squared equals, I'm going to say this is b times sine of theta times sine of theta. And to simplify that even more, before we do anything with the second half of the expression, I'm going to say that's b squared sine squared of theta. We put the 2 above the sine instead of above the theta. If the 2 were above the theta, then that would mean square theta first and plug it into the, take the sine of that answer. What we need to do is do the sine of theta first and then square that number. That's what this means. Do the sine of theta and then square that, square the sine. The next one is a little more complicated. I'm actually going to take the first one of the first number in the product and multiply by each of the parts in the second binomial. So each of these expressions both get multiplied by the entire expression here. So I'm using the distributive property, but it's a little more complicated. So to start off with, I have b times cosine of theta times the quantity, so this part times this quantity, b cosine of theta minus a. And since I'm distributing this, I now have to multiply by the a, so I say minus a times b cosine of theta minus a. It's becoming a fairly complicated expression, but it's nothing that we haven't looked at before. It's a lot more complicated. It's coming at us in a much more complicated way, but it's things that we have done before. So now I have two quantities in parentheses, and I'm going to use the distributive property on both of those. So I will say plus b times the cosine of theta times b times the cosine of theta. And I'm going to take a shortcut this time. I'm going to say b squared cosine squared of theta, using the same argument that I did for the sine over here. And I say minus ab, so I have b cosine of theta times a. I'll say ab cosine of theta. Then I have minus, and I multiply my a times b cosine of theta, ab cosine of theta. And you'll notice these two expressions are exactly the same. And ultimately, I have negative a times negative a gives me a plus a squared. And we should be starting to see some of the elements of the law of cosines. First of all, before I move on to the next one, I want to simplify this some more. So I noticed that these two were the same. I can say this is c squared equals b squared sine squared of theta plus b squared cosine squared of theta minus 2 times ab cosine of theta plus a squared. We will use that after we talk about there's a way to simplify this part of the expression. 7 and 8, questions 7 and 8 talk about that simplification. After we do that, we will use that to further simplify this. So, on to question 7. Question 7, we have a right triangle with a hypotenuse of 1. It's a very handy right triangle when you're talking about trigonometric functions. Fairly straightforward though. We need an expression for u and v in terms of theta. U and v in terms of theta. So first of all, u equals, you notice we have a right triangle, so we have our hypotenuse, opposite, and adjacent. So u, O over h, u over 1 equals sine of theta. Or I can just say u equals sine of theta. And when I do the expression for v, I have the adjacent and the hypotenuse. So v over 1 equals cosine of theta. Or I can just say v equals cosine of theta. Which is going to be helpful because in the next problem, we need to get an expression for cosine of theta and sine of theta. So sine squared of theta, cosine squared of theta. If we notice, I put in sine of theta for u, cosine of theta for v. I know that u squared plus v squared equals 1. So I can say that sine of theta, sine squared of theta plus cosine squared of theta also equals 1. Okay. Very important relationship in trigonometry. Any angle, if you square the sine, you square the cosine, you add them up, you get 1. And we are going to use that because we ended up having sine squared and cosine squared in the expression for c squared. So to ultimately finish out this problem, I'm going to factor b squared out of this expression. So I can say that b squared times sine squared of theta plus cosine squared of theta minus 2ab cosine of theta plus a squared. And this, we decided was 1. So I can say 1 times b squared, or c squared equals b squared minus 2ab cosine of theta plus a squared. And typically we rearrange that. You will see c squared equals a squared plus b squared minus 2